Okay, I guess we're back. Arindam? Arindam, are you there?
Hey, Mike. Yeah, I'm here.
Oh, okay. Yeah, our next speaker is Arindam Banerjee from the University of Minnesota.
All right, so let me, shall I share my screen?
Yes, please.
All right, I think it should be on. Hello, everybody. I'm Arindam Banerjee. I'm a faculty at computer science at the University of Minnesota. I'm going to talk a bit today about our project on physics-guided machine learning for subseasonal climate forecasting. I want to start off by acknowledging our team. So first of all, this project is getting funded by the Harnessing the Data Revolution program at NSF, and we are thankful for that. I want to acknowledge my colleagues and co-PIs, Ben, Tim, Rob, Pradeep, Becca, and Steve. We have been working hard at it. I'm going to summarize how much progress we have made. And I also wanted to thank my students, Shiji and Shinian, for helping us with the project at Minnesota. There are students at each institute working on this. So subseasonal climate forecasting. So if you think of these time scales, we typically often talk about weather forecasting. That would be typically the next 7 to 10 days. The next phase, let's say the 2-week to 2-month period, is what we would call the subseasonal period. And we are interested in forecasting key climate variables like temperature and precipitation in the 2-week to 2-month period. So this has been difficult, right? And this summary from a National Academy report actually shows the blue things you see are in the subseasonal range. So there's key applications in agriculture. You schedule the planting, you irrigate and apply nutrients. In water resource management, in maritime planning, you actually designate ship routes in this time frame, and aviation, emergency management, and so on. But the subseasonal time scale has been difficult to crack. So the NOAA Climate Prediction Center actually issues forecasts. So this was, the left-hand side is temperature, the right-hand side is precipitation. This was issued in July 31st. So this is for the month of August, a 30-day forecast. So if you focus on temperature, sort of the red regions are where the forecast is expected to be above normal. And the more red it is, that's the probability of being above normal is higher. The bluish ones are going to be below normal. And then the EC is that equal chance. From a machine learning perspective, you can think of it's like a 3-class problem. And these are the posterior probabilities of being above normal, below normal, or all 3 classes having more or less equal probability. And something similar for precipitation over here on this side. So how much skill do we have? So with these forecast models. So weather forecasts, we know that this is something we probably all use. We look up the weather and we know that probably for the next 7 days or next, at least 3-4 days, 5 days, it's pretty reasonable. But the weather forecasting skill actually drops pretty dramatically as you go beyond 7 to 10 days. 2 weeks out, it's not very good, right? And then seasonal forecast, actually, interestingly, we get pretty reasonable forecasts, broadly categorized as fair. So this is a schematic from the White et al. Summary paper a couple of years back. Subseasonal somehow is actually lower than even seasonal in some sense. So let's look at the sources of predictability to understand why subseasonal can be more difficult. So when you're looking at the next 7 days, right? So atmosphere has a lot of memory, and you should focus on the atmosphere and try to model the atmosphere. This has happened over the last 50 years with numerical weather prediction models. And this is sometimes called the quiet revolution. The state of the art is quite amazing, and we do a pretty good job over the next 7 days. For seasonal, ocean is the way to go because 6 months out, the ocean has that memory and you should be using ocean. When you come to the subseasonal time frame, it's a mix of everything. So you have a probably a little bit of the atmosphere lingering memory, and the land comes into play, and ocean should also be helping, and so on and so forth. So it falls sort of a mix of all of these rather than just atmosphere for weather and ocean for seasonal. So that makes it a little bit interesting. Now, let's try to understand why subseasonal is difficult for dynamical models like physics-based models, which are the basis of numerical weather forecasts. And then we'll also understand why it's difficult for machine learning. So if you understand this picture, the natural question to ask is that why can't we push numerical weather prediction models out to like 4 weeks, right? What would happen, right? So why can't we just run this thing out to 4 weeks and then use those? Well, one interesting property of these numerical weather for your dynamical models in general is that they can be chaotic. So if you're integrating them way out into the future, like 3 weeks, 4 weeks, they will have vast uncertainties and variations. Small changes will lead to large changes. So we all know that this has been developed over probably starting from the 1960s. There's a very rich literature in there. So that's the reason why the numerical weather prediction models are actually not quite usable out there 4 weeks out. So let's take a closer look at this, right? So this model is the so-called, this is developed by Ed Lawrence, and who's behind a lot of these threads, initiating these threads. So this is called the Lawrence 96 model. It has two sets of variables, the x's and the y's, and they have advection and diffusion, and x's and the forcing, and they're coupled. So we don't have to sort of understand the nitty-gritty of these PDEs, but for our purposes, we are going to call these x's as the atmosphere and y's as the ocean, in the sense that the x's have fast dynamics, they're quickly changing, and y's have slow dynamics, and they're slowly changing. And when it comes to sort of, subseasonal, both of these come into play. So this is, remember that we said that the orange is the atmosphere and then the blue is the ocean. So this is how the dynamics play out, right? So if you see orange is the atmosphere, you see how fast the dynamics are for the atmosphere, this fictitious atmosphere, and how slow dynamics are for the ocean. So you have a better chance of predicting or forecasting the ocean compared to those orange wiggles. But when we are in the subseasonal range, we have to probably do both or a mix of the two. So this is the challenge, right? Why is it challenging for machine learning models, right? So there's a vast array of methods for multivariate time series forecasting. Like you can do auto-regression, you have a Y time series, you predict the next time step, or you can use some combination of exogenous variables or covariates, or you can even have latent variables like Z's, which you don't observe, but they are affecting what you observe. So hidden Markov models, Kalman filtering, data assimilation systems. And then there is an entire suite of deep learning methods like CNNs, RNNs, and whatnot, autoencoders. The challenge is really, we are not trying to predict YT plus 1. We are not trying to predict tomorrow's weather. We are trying to predict the weather 30 days now, right? So you see this YT plus 30 is a different beast. And if you do a very naive training exercise, what will happen is that you will do very well on the training set. It will be a complete disaster on the test set. So it's very easy to overfit because the amount of predictability that's left is very minimal. So you have to be very careful what you can predict 30 days down. There are other challenges. There is a pretty steep baseline that you have to beat, which is the climatology. So let's say our prediction task is temperature in Minneapolis on September 18th, 2020, exactly 1 month down. So today is August 18th. The baseline method would be the 30-year average in Minneapolis on September 18th, right? So that will be our forecast, right? So we average over the last 30 years, and if you are developing a method for this task, you have to be able to beat this. This is an extremely steep baseline because it summarizes what has happened in the last 30 years. So there is a strong baseline to beat. The other thing that happens in forecasting models is that we are supposed to, given the data, we are supposed to apply a method to the data and get the outcome. What we often end up doing is that given the data, we apply the method, we get the outcome. We look at the outcome, we don't like it, we come back and tweak the method and apply it again to the data. And this goes on till we are happy. Unfortunately, the test set has been contaminated with this adaptive data analysis. This has plagued machine learning over the last 10 years. If you look at Kaggle competitions and so on and so forth, this is one of the biggest reasons. It's not which method you're using, that things break during test time. I'm citing a beautiful blog post by Moritz, probably 5 years back now, but this is still relevant. So if you're getting into forecasting problems, be very aware of this. A good development has happened in ML on adaptive data analysis and how to avoid it. And then we need to quantify uncertainty. So nobody's really looking for a temperature in Minneapolis 30 days down, but you have to be able to characterize the distribution, which is what we saw from the NOAA setup. All right, so there are a lot of challenges, and we are at the early stages of the project. So what we decided to do early on is that we defined a concrete problem. Let's say we are going to forecast the average temperature in weeks 3 and 4 out. So sitting today, we look at weeks 3 and 4 out, and then we look at forecast the average temperature. And we looked at continental US. So this is like a 2-degree latitude longitude, close to 197 locations. And then we residualize with respect to climatology, right? So we basically remove the 30-year average on each location and date. So what you're left with is the residual signal that you have to forecast. And if you're able to forecast that well, then you are of course going to be doing better than the baseline, which is climatology. In terms of the covariates we used covariates from the atmosphere, land, and ocean. We use geopotential height, relative humidity, sea level pressure, Madden-Julian oscillation. These are atmospheric variables or processes. For the land, we use soil moisture. Ocean, we use sea surface temperature globally, and the NINO indices, multivariate Ansu index, and the North Atlantic oscillation. And then for machine learning models, we basically threw the entire set at it. So gradient boosting, linear models, lasso, multi-radar, AutoKNN. This is developed by some of our colleagues, a paper in KDD last year. Deep learning models like the usual CNN, then CNN LSTM. We developed a variant of this encoder-decoder model based on LSTM encoders and neural network decoders. And then a bunch of climate science baselines. So damp persistence, which is from this beautiful book on short-term climate forecasting by Van den Doel. Climatology, as I said, and something simple like a least squares using the NAO, the North Atlantic oscillation, and the NINO indices. So this is something simple you can quickly run and see how well it performs. So we're going to look at the results. So this took us some effort to do, but sort of the evaluation was based on, let's say location 1 is Minneapolis, and we have trained it on the past 30 years, and the validation on hyperparameter tuning has all happened in the last 30 years. And then our first forecast is going to be weeks 1 and 2 in 2017. And then we shift everything by a week, and then we forecast weeks 2 and 3 average temperature 2017. We keep doing this for over a period of 2 years, right? So this is sort of how we are going to be forecasting a time series, and then we can also look at the evaluation on that 2-week period and all locations. So that will be sort of the spatial performance in that 2-week period. So for the purposes of this talk, I'm going to show you results on the temporal Gaussian similarity, basically the prediction performance over that 2-week period, over each 2-week period over 2 years. And then Y star is the ground truth. Remember, the ground truth is deviation from climatology, so it's the 30-year average. And then Y hat is we are predicting the deviation, so we're computing cosine similarity. So we are looking for positive cosine similarities, right? So if it's negative or zero is basically climatology. If it's negative, we are doing worse than climatology, and that's no good. Results. So green means we did good. Red means we did not do good. There's a whole bunch of methods I'm showing over here: XGBoost, lasso, deep nets, and other things. The good news is that we actually seeing a lot of green. So there is promise, there is hope over here, right? We will be able to, so if you look at the performance of XG gradient boosting or lasso or these deep nets, more or less they are overall positive throughout the US. Something like CNNs did not do very well, and we have been looking into that. CNN LSTMs did a little better, least squares with NAO. So this is overall good news, is that even on the residual predictions, machine learning models hold a lot of promise. And we are hoping over the next year, we will be able to really push these methods forward and develop more specialized methods, which is going to do well. But the top row, really, the gradient boosting, a nonlinear method, lasso, which is a linear method, and the encoder decoder, which is a deep learning method, all did actually quite well in our setup over this 2-year period. there is clearly room for improvement. So what we are focusing on right now is to release our entire code base and data set so that the community can take a crack at it. I think it'll be great if more folks got involved and there'll be better ideas and so on and so forth. But one interesting aspect of our work has been looking at what helped, what are the sources of predictability. You remember the schematic from one of the earlier slides. So we started investigating which features were deemed important by the models which did well. Right, so we looked at gradient boosting and linear regression. Broadly, what I'm showing is that for every feature, a darker color means that that was deemed important. The importance here is getting measured by Shapley value. This is a sort of a now popular method of evaluating feature importance. You could use other methods as well. We have other results in our paper. So what we are going to do is that we are going to see which of these features came from the ocean and the land and the atmosphere, just to understand who contributed the most. And when you look at the spatial features like SST and so on and so forth, we did not use the actually latitude, longitude. We use the top 10 principal components. So that's where the PC1 through PC10 are. Those are the principal components of these. Okay, let's see which things got picked from the ocean. So the models, both of these models sort of felt that SST in Pacific and Atlantic are important. The NINO indices, NAO indices are important. So those got picked up one way or the other. You will see that Lasso is picking things a little bit, it selects certain features, so it does not pick uniformly. So that's the nature of Lasso. Gradient boosting is picking them more or less. It considers it important. What about land covariance? So soil moisture got picked up by both of these models and they did really well. They think soil moisture is actually important. What about atmosphere? Well, you know, what remains is atmosphere. Right, so you can see that it's pretty light in color. So atmosphere was not really helpful, except for maybe the Madden-Julian oscillation, right? So Lasso definitely thought the MJO phase helps. Gradient boosting thought, yeah, MJO is actually helpful, and maybe a little bit of the geopotential height. So we'll talk a bit more about this in a moment. But this is actually one of the more important parts of our studies, that we are trying to understand the sources of predictability. So now coming to dynamical models, like what role do dynamical models play, right? So shall we redefine the goal? So we said that if you run the dynamical model out 30 days, this full dynamical model, it's going to get chaotic, we are not going to get things. So what we have been thinking and brainstorming about is that instead of trying to recreate the all states and all variables, let's try to identify a subspace with memory. And focus our efforts, you know, tuning the model, parameter tuning, estimation, and so on and so forth, on things which are important. So maybe we want to get the SST right, maybe we want to get the soil moisture right, and so on and so forth. So rather than running them forward with, you know, just like we do in weather forecasting, we are going to look at the subspace, which actually helps us with our task at hand. So we want to briefly touch on what happens with, you know, SST and soil moisture. So SST, if you let's say take Ansu, right? So there's a lot of ongoing work, you know, at Columbia IRI and the NOAA CPC. They do release these forecasts based on both dynamical models and statistical models as to how, you know, the Ansu index will look like going forward. You know, this is the current forecast. So you can see that it's going negative. So probably La Nina phase coming, going to start, and so on and so forth. The goal would be to carefully look at these models and see if we can sort of improve them, maybe using machine learning, and some of this work has already started to some extent using deep learning to improve Ansu forecast. Our time scale is a little different, so we'll have to keep an eye on that. For soil moisture, really this is how soil moisture maintains memory. So there's a precipitation event, and then soil moisture creates that memory which stays for about 2 weeks. Then we have to then focus on, we need these extreme precipitation events or high precipitation events. This is one of our targets. And you know, we have been looking at processes which can potentially affect those precipitation peaks. So Madden-Julian oscillation plays a role. So there's a suppressed phase and an enhanced phase is moved eastwards. When the enhanced phase has high precipitation, and when that comes on top of the US, we probably get high precipitation events. And I think we will probably hear about MJO later in this workshop for folks who are experts in this, but we have been eyeing this as well. And then just to model the soil moisture itself, we may have to look at hydrology model, watershed models. I think we may hear about those as well in this workshop. But broadly, we are trying to discover and forecast other sources of predictability. And then the effort in dynamical modeling would go towards improving those rather than these millions of variables that we are interested in. So this sort of redefined goal sort of gives us a target for how do we do model tuning or parameter estimation in dynamical models. So as an example, say going back to the Lawrence 96 model, this model has 4 parameters, and we would like to sort of know the values of f, h, c, and j to get a certain task done, like some variable like we were talking about before. The problem over here is that with these kinds of dynamical system parameters, you cannot do gradient descent. You have to understand that, right? So in machine learning, we often do gradient descent because for a fixed set of parameters, you can integrate the model out and see how it does, whether it agrees with observations or not. But really, you cannot then take gradient with respect to f and h. So whatever we do has to be a derivative-free approach in order to estimate the parameters. So we are actually currently actively investigating multi-pronged approach towards doing this. There is some method of moments approaches which have seen some success, and we are investigating those. We have been investigating Monte Carlo tree search. So Monte Carlo tree search, in case you don't know, sort of gets a coarse-grained sense of which regions look promising, starts digging deeper into those areas and deeper into the areas which looks most promising, and so on and so forth. You may have heard of this in the context of AlphaGo. So MCTS was one of the driving forces behind DeepMind's AlphaGo system. We are now looking into MTCS for parameter estimation in dynamical models. And we are, of course, looking at the more traditional literature in derivative-free optimization. And there's some initial promises, but these are high-dimensional systems. So there's a lot of work going on currently. Hopefully, in another 6 to 8 months, we'll be able to share more about how these results look. But very deep into machine learning methods over here on the parameter estimation front.
Arindam, could you wrap up? And we have a couple questions.
Yeah. So just to wrap up, as Michael said, so the outlook we have is that, remember this picture. So subseasonal range, it's a mix of atmospheric processes, land and ocean. And we are trying to identify sources of predictability. And ML models are getting good accuracies, but they are also helping us identify sources of predictability. And then we are sort of conceptually taking those and coming to the dynamical models and engaging in parameter estimation in those dynamical models in order to basically improve the forecast of the sources of predictability. So we want to really help improve, SST, MJO, and other things. And the parameter estimation is using a lot of machine learning methods in there. So this is sort of the high-level outlook. I think we have initial promising results. We believe ML models will be able to actually push the state of the art, but we definitely need help from the dynamical models in order to sort of improve forecasts of those sources of predictability. And in a way, we would like to hear from other people who have expertise in these things. If you have suggestions, pointers, we can talk. And we are working to release our code and data by the end of the year. It will be a pretty large data set for people to play with. That's all I have. Thank you.
Thank you, Arindam. First question. What about employing some probabilistic graphical/causal inference models for such subseasonal forecasting?
Yes.
Could you also test them?
Yes, we are actually currently working on, so coming back to the challenges I talked about, we definitely don't want to do point forecast. You're absolutely right. We have been investigating on the side deep generative models, but trying to build in calibration and other guarantees in them. But once they're ready, we are going to hopefully start applying them by probably later this year. But they have to be properly calibrated. So this is something we are keeping an eye on. But this is an important direction to go. 1 month down, nobody's looking for a point forecast. We need probabilities.
Okay. Second question. On ML for SSF data and model slide, can you explain what residualizing with respect to climatology means?
Sure. So we take let's say we take the data, the raw temperatures, and the example I was giving is Minneapolis temperature. Let's say we are looking at September 18th. So what we do is so let's go back a couple of slides. There you are. So we take the 30-year average from 1990 to 2019 in Minneapolis, temperature in Minneapolis, right? And that's sort of our climate-related forecast next month. And we basically subtract this, right? This is free lunch. So you can subtract that. The deviations from that is what we are interested in predicting, right? The deviation from climate change. So what we mean by residualization is in some sense like a z-scoring, where you're subtracting the 30-year mean and also dividing by the 30-year standard deviation on each location and each date. So the final prediction is on the residual. This is actually important to do, because if the temperature is 65, you're predicting 63, it will look good, but maybe climatology is actually better, right? So you want to make sure your baselines are actually really good. In this case, it is easy to do. So that's what we mean by residualization.
Okay, thank you, Arindam.
Yeah.
Our next speaker will be Laure Zanna from NYU.
Okay, great. Thank you very much to the organizer for having me. Pretty exciting workshop. So I'll be talking about some work we've been doing with my former PhD student, Tom Bolton at Oxford, who's now graduated, and a postdoc, KGML at NYU, who started a little less than a year ago. And the main motivation of our work is trying to represent processes that are not included in climate models, and especially here, I'm going to talk about the oceans only, and using machine learning to actually represent those processes that are in there. So just to motivate this picture that many of you, might have seen if you look at ocean models. So it's created by the Met Office. We're looking at ocean surface currents from a model. And that model is run at 3 different horizontal resolutions. So on the right over here, it's run at 1 degree resolution. So basically grid box size about 100 kilometer by 100 kilometer. Then as we increase the resolution, so now 1/4 of a degree, resolution is about 25 kilometer at that point. So you can see more turbulent features, more filament. It gets a lot messier. So there is more physics being included as I increase the resolution. If you increase the resolution even further to 1/12 of a degree, about 8 to 10 kilometer. So now you can see kind of sharp jets like the Gulf Stream detaching from the US East Coast, a lot more turbulence, a lot more physics being resolved. And it's not just that the picture looks prettier, is that we are more truthful to the physics that basically is encapsulated within the governing equation of our climate system. And that means that when I resolve more of the physics, more of those small scales, I have a better representation of ocean currents, their variability, the way the ocean takes up heat and carbon, so all those things that are quite important for the climate system. So now the main question we're trying to address is, how do I represent those processes that are not resolved in those kind of coarse resolution model on the right, but without the computational expense of running at that very, very high resolution? So that's what I'm going to discuss. So I'm going to start with a little bit of an introduction and kind of motivation, but I knew I was coming after a few people will talk about climate, so I'll go a little fast. So basically, what do we do to model the ocean and atmosphere system? And then slowly talk about what we call the closure problem. So basically how to represent those physical processes that are not included at coarse resolution. And so I'm going to do a little bit of a, then, now, and next in terms of what I think we've been doing and the way we should move forward, and hopefully kind of give you a broad idea of how to tackle this problem. And I'll showcase 2 examples today on how we can use machine learning to actually improve either our knowledge of the ocean or the ocean dynamics, and how to improve the parameterizations at the same time. So there'll be 2 examples. One is called equation discovery. So we're going to discover differential equations using machine learning for those processes that we can't represent. And so, the beauty of that is you have a mathematical expression. So, technically you can explain it and you can represent it and all those things. So that's great. We usually feel quite happy about this, and it's computationally cheap. The second approach, and that was basically led by Tom Bolton when he was a PhD student. And the second approach is using deep learning, so convolutional neural network, which are a little bit more black box, but here we're trying to be more truthful to the physics, in the sense that turbulent processes are not deterministic. You don't have one value of the turbulence for one value of your large scale flow. You actually have something that is not deterministic. So here we're going to modify the neural nets So then we're going to predict both, mean value for that missing forcing, but also a standard deviation. So we're basically going to try to capture this randomness, if you wish, of the turbulent processes as we go. And I think if there is one thing that I would like you to, to remember at the end of this talk, if you don't remember a word of what I say, is just that, if you merge diverse approaches and way of thinking, that's one way to move forward. And I think that's an important way to move forward in terms of modeling and understanding climate system. There's not one great approach or one great method, whether it's theory or machine learning or whatever. There are many of them, and kind of, keeping an open mind and using tools for the problems that you're trying to tackle and trying them out and seeing if you're learning something new. And if you can, discover something new you didn't know before, then we should use it. And I'm saying that because I was trained as a dynamicist, not as a machine learning person. And, a lot of people on the dynamic side don't like machine learning because they think it's a black box, but I think they can teach us a lot of things we didn't know before. And so keeping an open mind, I think, is important. Okay, so if you know nothing about the climate system, basically what we have is a bunch of partial differential equations. So here it's kind of a way to represent them. So this is for momentum. We have an equation for the density of water and for the temperature and salt in the interior of the ocean. And you'll get a bunch of equations like this, for the atmosphere, for the fluid in the atmosphere, and a bunch of other equations for different components of the climate system. Now, for the fluids part, we have the equations. So technically, if we could resolve them on the computer with all the resolution in the world, then we know how they're supposed to evolve. Of course, we can't really. Those are kind of nonlinear equations. We don't have the computing power to actually resolve those equations from the millimeter scale all the way to the large scale, climate scale type problems that we're thinking about. So we just can't do that, right? So how do we deal with this? What we do is we're gonna basically take those equations and break them down into little pieces. And so we're going to solve them on a grid. So this is our sphere. The ocean is going to be broken into little pieces, same for the atmosphere. And within each one of those little pieces, the size of that box, we will resolve the equations that we have. But of course, now we have a modified equation because there are a lot of scales here. So in these kind of little diagrams that are fast and small. So this is length scale, this is time scale. So those kind of small scales that are below the grid box size of the model that I'm considering are not represented. And so usually, typical resolution of a climate model is about 100 kilometers or so. Nowadays, we have about 20, 25 kilometers, for some of the state-of-the-art coupled climate models, but they're getting more and more expensive, right? The more stuff you have in them, the higher the resolution, the harder it is to run them for hundreds of years or have many ensembles. So, we're stuck. So what do? We truncate at a given resolution. Everything that is below the resolution of the model that we're considering is basically out. And all those missing processes are actually important because they impact the large scale dynamics as mentioned. So again, they will have an impact on sea level, on the amount of precipitation you have, on how much heat the ocean is taking up. Marcus mentioned, basically how much the land will take up carbon. All those kind of things are basically encapsulated in those small processes because they interact with the large scale, but we don't have them. So how do we deal with that? Well, we have to come up with a way to represent those subgrid processes. And that's called the parameterization or the closure problem. What we need to find out is a function, and that function is going to have basically resolved quantity. So basically, it's going to depend on the scale that you can resolve in the model. And I have a bunch of parameters as well. And so here, I'm going to showcase how we deal with the parameterization problem. And I'm going to focus on the problem of ocean mesoscalities. So they're basically ocean processes with a scale of about 100 kilometers, kind of represented here and over here. So this is the Gulf Stream. You get those kind of turbulent features that are being shed off a strong jet, and they feed back momentum and energy into the mean flow. So even though they're small scale, they kind of impact the large scale as well. So that's what we're going to focus on. And we're going to focus on how do we deal with this problem of parameterization? How do we represent that function here as a, with parameters and resolved quantities? Okay, so that's kind of the ultimate way people have been doing it. So what I call the traditional approach or the physics-driven approach. So what people do is we started with theory. We said, oh, well, basically eddies usually mix things around. So mathematically, you can write them as something that looks like diffusion, with a parameter in front of it. And so that, that's basically kind of a physical understanding of what the processes are doing in its bulk approach. And then what you do is you take that, that expression, which is a nice mathematical expression, and it's kind of fairly stable, and you plug that into a model at coarse resolution. And hopefully, you end up with a system that is more representative of, the state of the ocean. You have less errors in your climatology, in your temperatures and other fields. And so you compare that with, some observations. As you go back in time, we had less observations. Now I'll talk about, what we have now. But overall, this is the way you evaluate your model. You come up with a theory, you can write it down mathematically, you put it in your climate model at coarse resolution, and then you evaluate against observations. Now, the other extreme, and so some people have talked about this, is kind of black box approach, or the machine learning approach, which theoreticians usually don't like very much. And here, the situation is a bit different. What you do is you start with data. So now, what is different than what we had before is now we have some high resolution simulation. We just don't have a lot of them, and we can't run them for long time scales, and we can't have ensembles, but we have a few of them, some idealized, some complicated. And so we could learn from that high resolution data. We also have a lot more observations than we had before, especially in the oceans. We get data from satellite altimetry. We have those floats that are called algo that basically profile the ocean down to 2 kilometer depth, gives us a wealth of new information. And we have some creative ways to use elephant seals that can dive at high latitude underneath the ice. So we're getting, a new wealth of information that we didn't have before. So now it's kind of time to use that new data with, of course, the advance in machine learning, which are faster algorithms that know how to capture, both temporal and spatial information in a way that we didn't have before, and come up with a new parameterization now that, again, will do the same. We'll put in a coarse resolution model and hope that it will improve, your simulation when you compare them against the high resolution or the observation. So you continue to evaluate against that. But that's, as I mentioned, so this kind of physics-free or black box approach is less exciting in a sense, because you have no idea what the algorithm did. You didn't tell him anything about the physics, or he didn't teach you anything about the physics. So there's a little bit of reluctance in going that way. And so in the last couple of years, I guess, quite a few of us, both in the ocean and the atmosphere, have been embedding physical constraints within the algorithm. So Vipin mentioned, we call it physics aware or physics constrained or physics guided. So here the idea is the same. We start with data, observations of models, your algorithm, and you embed some kind of physics within the algorithm. So, here's an example of an architecture of a neural net where we embedded conservation of momentum. So, so we make sure that momentum get redistributed and not being created out of thin air. And that helps with the stability when you plug it back into a coarse resolution model and evaluate against the data set that you started with. We've been taking things one step further, which is trying to make things interpretable and physics aware. And I think that's where things are moving forward, or at least that's the way I'd like to see them move forward, and where we're putting a lot of effort, which is starting still with the high resolution and the observations, continuing using those great algorithms that are faster, need more or less data that can generalize, adding physical constraint, but being able to extract something that could be a theoretical basis to enhance knowledge, not just coming out with an expression with millions of parameters that I can't do anything with, but coming up with something that is truer to the physics and will actually explain, more than I knew before I started. And hopefully teach me something about the dynamics of the ocean that I wasn't able to capture with my initial theories. And of course, the hope is you can put that into coarse resolution climate model and improve on those simulations when you compare them against. Okay, so that's what I'm going to try, to showcase with those two examples. Trying to enhance knowledge or be truer to the physics that we can extract from data and from those high resolution simulation using machine learning. Okay, so as mentioned, I'm going to focus on ocean dynamics. So mesoscale, 10 to 100 kilometer resolution roughly, they impact the large scale flow. So example one is going to be this data-driven interpretable equation discovery. So we're going to learn a differential equation for the ocean physics for the part that we don't resolve. Only the part that we don't resolve, right? I'm assuming that I know everything at the larger scale because I can resolve it. And the example number 2 is going to use kind of the more black box approach, but again, trying to remain true to the physics, the fact that turbulent processes are not deterministic, they're stochastic. And so there we're going to modify the way we optimize the algorithm to include those approaches. Okay, so example number 1 is this kind of data-driven equation discovery. So what do? We're going to take a very idealized simulation of the ocean because we need to start somewhere, and we're going to feed the algorithm resolved quantities, so coarse-grained quantities from that high-resolution idealized simulation, and we're going to diagnose the missing forcing from that high resolution that I should put in a coarse resolution, if I wanted to perfectly represent those missing processes. So I'm going to try to learn, things that are not resolved at coarse resolution by using data from the high resolution simulation. Okay, so we're going to feed that into the algorithm. So now what that data, driven equation discovery algorithm wants, so it wants those resolved quantity that you would have in a climate model, like the velocity fields, but it needs to learn equations. So, it's not like us, but the algorithm is not going to think about which equation. What it needs is more data to show what the mathematical quantities look like in terms of data. So what we give the algorithm are more pictures, more pictures of data that will represent part of the physics that are important. So it's going to be the divergence and the vorticity and the sharing deformation. So all those processes, if you're not a dynamicist, they all linked to instabilities of the fluid, the way eddies are extracting energy and momentum from the mean flow, and the way they feed it back into the mean state. So it's all those mathematical properties that, of course, we're not giving it as equation. We give it the algorithm, just that data, those images that are the divergence, the vorticity, and the sharing and stretching of the flow. And we give products of it or higher derivative of those quantities. So we're going to build a library of function that is created from those 4 quantities that are key physical quantities to the ocean mesoscale processes. And we're going to let the algorithm basically prune through that library of function. So we're going to use a method that is based on relevance vector machine. So it's a sparse Bayesian learning algorithm. So this paper here actually kind of was the inspiration for it. And here, what do we do? Well, the algorithm is going to go through that full library of functions. So, we have dozens of functions that it goes through, and it's going to prune by, adding weight to each one of those functions. And then based on the threshold, removes the one that have nothing to do with, the images of, or that can reproduce the forcing we're trying to represent, and keep the one that could. I'm going to go through that iterative process many, many times. And they're going to come up with basically a final set of weight multiplying the library of function that we want, and each weight will have an uncertainty associated with it. So that's also a plus. You get an uncertainty associated with each one of the weights. Final product, we built a library of function that all of those functions should be written as the divergence of a flux, which means that we've embedded within the math, conservation of momentum. So what do we get? Well, we get basically sum of weight multiplying, a few functions. And so what we've done is we ended up with weights multiplying functions that were, and the weights were quite close to one another. So we decided, just for the simplicity, to combine them into one mathematical piece. And I'm not going to go through what it means, but all we end up with is basically one parameter, kappa, which has an uncertainty of about 10, 15% or something like this, multiplying by the divergence of a symmetric stress tensor. And it's not something that we built in. So here we have a nice, concise mathematical expression for the missing forcing that we should put in a coarse resolution ocean model that represents the effect of mesoscale on the large scale flow. And we only learned that from idealized high resolution data. We were quite happy with it because we could interpret some of the physics behind it. And again, I'm not going to go through it, but it has the right properties of something we needed, which can extract momentum from the shear of the velocities. And again, I'm happy to answer a question for anyone who's interested. So now let's do some validation offline. So validation offline just means that, I kept half of the data on the side and I'm comparing the skill of my algorithm. So that model was very idealized. And just to give you an idea, so this is the mean forcing. So in that model, we have a jet in the middle. So the forcing is high where you have a jet, where there's a lot of turbulence, and that's the standard deviation. So we compare our equation discovery, which is here in the middle, with a physics-driven parameterization that we actually come up with a few years ago. And so let's just look at the correlation between the forcing that is directly diagnosed and the truth. So you can see that our physics-driven offline doesn't look quite good, right? Basically, it's like anti-correlated, in large chunk of the domain, but does a decent job in other parts. If you look at the equation discovery, the correlation is quite uniform, so it's positive everywhere. Seems to be doing pretty good job, in a large part of the domain. And we compare it to a convolutional neural net in which we built in, a physics constraint where we conserved momentum in it. So now you can see that the correlation from the neural net is much higher than the equation discovery, of course, the physics-driven part. So really much higher, but worse in regions where actually it's more wave-like, where there is less turbulence. So it doesn't do as well in generalizing to places where there is less turbulence, but it does much better than in other places. Now, if you plug that online in a model, then all bets are off now. So, we saw the plus and minuses of the equation discovery. If I plug that into a coarse resolution model, then again, all bets are off. All parameterization blow up. So that's, thing number one. So it's not because they did a good job offline that they will not make your model blow up. So in our case, they all blew up. So we had to tune down the parameters. Overall, the neural net did better than the equation discovery. So the equation discovery is this kind of red line over here. And I'm plotting the total amount of energy in the flow. It's simply because we couldn't push it higher up. There might be many reasons for it. And again, I'm happy to talk about it later. Okay, and so the last kind of showcasing before I close is just this idea of learning from higher resolution data. So now we're gonna learn from a global climate model, not idealized cases anymore. And we're gonna use a neural net to predict the mean and the variance using basically a modified architecture of the convolutional neural net. So now we're not using idealized data anymore. We're using global climate data from a very high resolution climate model, the GFDR model. And I'll just play the movies. So this is the predicted forcing from that high resolution simulation. Hold on, yeah, it plays on the left, and on the right is the prediction. So it does a pretty decent job everywhere. But we also learn the standard deviation. So now we're not just learning the mean, we're also learning the standard deviation of that forcing. And here again, it does a pretty decent job. Okay. So I'm going to close up.
We have a couple of questions.
Closures are still, basically going to be in high demand for many years. Our view is that they should be physics aware, interpretable. You should be able to actually understand what you're doing, and it should generalize to different climates, right? So here I presented things like constraints of energy, momentum, ways to represent stochasticity. But I think one thing that I want to, again, want to say, if you remember nothing from my presentation, there is more than one way forward. And so exploring and merging ideas, whether it's discovering equations or coming up with a new theory, or adding randomness or stochasticity, all of them are important. And this kind of combining simulation, observation, theory, and algorithm should be the way forward when we want to improve climate modeling. And I'll leave it at that and take questions if there are any.
Okay, thank you. The first question: after you reach an equation with one unknown, couldn't you use regression to find the coefficient?
Okay, so it's not, so we're not, so there is an iterative process, right? But so basically the algorithm, the way the algorithm does it is like it prunes all the terms at one go, then remove a few and then continues. You could, learn with one, but what was interesting is, the algorithm was able to actually select one or two at the same time that will represent, already 50% of the variance. I'm sure we could. I think the algorithm is definitely more efficient than us at doing it. So, I let it roll with it to see what we could discover.
Okay. Second question. Predicting climate signals is exciting. Are there advantages to combining physics and ML to understand and predict extreme climate events?
Yeah, absolutely. So here we've been focusing on this kind of parameterization problem, which is kind of the turbulence problem, or we've been predicting the first and the second moment, if you want. So now the third and the fourth moments, skewness and kurtosis, which are your extremes, are, is one step further. You need more data. You need to be a bit, You need to have better tools, but this is something we're exploring. And I agree, I think there should be a lot more on this topic because that's what people care about as well.
Yep, thank you. Okay, let's move on to our last talk from Ansu Chatterjee, the University of Minnesota Statistics. Oops.
Sorry, I had muted myself. So thank you, organizers, Michael, Vipin, Laura, everybody. And so I'm Ansu Chatterjee from the School of Statistics here at the University of Minnesota. And that was a set of 5 brilliant talks up to now. And my talk is slightly different. So what you heard from the previous speakers were very, very interesting applications, very, very interesting forays into using science for building better machines, using machine learning for better understanding of science. And so that there was a lot of development on the interplay between science and machine learning. I'm going to go a little bit deeper into the foundations of it. Why does that happen? Why did the system of equations that Laure showed just now, just a little while back, why did it work? Why did a deep learning model actually work? So here's a lot of maybes. This is a theoretical work. Also, as a theoretical work, I should have had a lot of equations, and I've sort of deliberately tried not to have equations out here. I know you lose half of your audience with every equation. So, so before I get there, let me just up front, I'm part of a different HDR grant, Harnessing the Data Revolution grant. I'd like to acknowledge that, along with other grants from the divisions of mathematical sciences and DMR. So you could learn more of our projects from these links. And as I was saying, this talk is mostly an overview. I'm not going to present new results, essentially. And this talk includes work from a lot of different groups. And what I'm going to do is we're going to explore the different ways deep learning, in particular deep neural networks, DNNs, relate to things that would allow you to do uncertainty quantification, that would allow you to discover equations, as Laura was doing, that would allow you to combine different varieties of doing machine learning, or like the way Arindam, Anuj, Vipin, everybody else was doing. So, and here's a bit of a shameless plugin to begin with. If you are affiliated with the University of Minnesota, there's a class that I'm teaching next semester, beginning in just a few more days, Statistics 8931, which is on the foundations of data science, which would have way more details than what I can present in 15-20 minutes on essentially exploring the connections between machine learning, AI, and other fields of data science. All right, so let's jump in. What exactly do we know about deep neural networks, and why do we bother? Why would we want to study a link between deep neural networks and, for the purpose of this talk, Gaussian processes? You could already see from the work Arindam presented, Laura presented, that there are connections, there are things that you could just build into the algorithms. So deep neural networks have certain fantastic performance demonstrated in tasks that are essentially discriminative. I mean, it can do great in distinguishing cats from dogs, or in being able to say where a boundary of two blobs of different colors lie, and things like that. So that's what deep neural networks are really good at in many contexts. It's essentially also a black box. So why are we here? We are here because just being able to say this is a picture of a cat as opposed to that being a picture of a tomato is not really sufficient. We are here, this whole thing Vipin and his group has organized is because we would like to leverage that in order to do science. And we'd like to use science in order to help us build better algorithms. What we are aiming for here is interpretable deep neural networks. So in order that deep neural networks are useful for doing science, we need to be able to understand what exactly is happening inside that particular black box that we're building. So that's the purpose of this workshop. That's the purpose of a lot of this harnessing the data revolution HDR grants have been working on. And so here's a bit of an entry into that world. So in order to get there, in order to help us understand what's happening inside a deep neural network, we need to be able to relate that to the scientific method. We need to understand what kind of features is it picking up, or upweighing or downweighing. Also, this is something that Arindam brought up, and then Laure, of course, brought up. We should be able to do more science, understand more than what we had put into the deep neural network about. So that relates to being able to test a scientific hypothesis, being able to frame new hypotheses, and very, very, very critically for doing any science, not just the ones that were presented, but everything, whatever we do with deep neural networks needs to be reproducible. Now, all of these goals would be met if we could actually associate a probabilistic framework with deep neural networks. And that's the reason why looking at the connections between deep neural networks and probabilistic systems, and I'm just illustrating things with the most prominent one that's out there, Gaussian processes. That's why we study that. All right, let's see. Okay. So part of what we know is that, did I move a slide? All right. Is that all right. Yeah, so what do we know about deep neural networks or artificial neural networks in general? Now, something that has been known for a very long time, for decades now, is that if you take a shallow network, a two-layer network, so basically meaning only one hidden layer, and make it infinitely wide as you would like it to be, you could pretty much approximate any continuous function with arbitrary degrees of precision using that particular neural network. So that has been known for a while. And this is a deep field of research. People have been showing that you could do the same thing with a long, narrow network. So arbitrary depth, but each hidden layer in a neural network is narrow, it's bounded. And here's a typical result. And I actually, if I click there, I'm jumping in. So by the way, anytime I present a theorem or something like that here, I'm not stating all the conditions. So don't jump at me for that. So let's say you have got a probability distribution sitting on so a discrete probability distribution sitting on like 2 to the power n points. You could train a deep belief network, which is not particularly popular these days, but it is another kind of a artificial neural network with about 2 to the power n minus 1 depths, that could get arbitrarily close to this. Okay, so a deep but narrow network does work. It also does not require more parameters than what a shallow, wide network would do. So these are the kind of theoretical results that have been developing. And some of these are coming out even now. One got published, a really good one got published last month. So what is this universal approximation theorem that artificial neural networks do apparently satisfy? At least some of them do. So it's kind of a baseline thing, something that in a statistics or in a probability community sort of corresponds to being asymptotically consistent. If you cannot do it, you're doing something wrong. So that's the first step. But this particular angle, universal approximability, does not actually tell us anything about either the interpretability, rate of approximation, uncertainty quantification, and stuff like that. So what else do we know about shallow, wide networks? And this is something that Radford Neal, who's actually a very, very brilliant person, contributed tons to this field, came up with in his thesis, that if you take this 2-layer network infinitely wide, what you're pretty much doing is you're doing stuff that a Gaussian process would do. So there is a connection between the shallow, wide network and Gaussian process. So that's the other connection through which we actually get into a probabilistic framework. So I know there are hundreds of people in the audience, and many of them are students. So let me just do a quick one-slide introduction of what a Gaussian process is. It could be defined over any domain. Think of time as an example, but pick your favorite domain. You could pick any Euclidean space. You could pick any manifold, anything. The big deal is that you should be able to define a positive definite function over there, meaning that anytime you construct matrices of this sort, that should be a positive definite matrix. If you are able to do that, and your stochastic process is such that pick any dimension, pick any set of points that has a multivariate normal distribution, a Gaussian distribution, you have a Gaussian process. So deep neural networks relate to this object. So again, just to recapitulate, deep neural networks have excellent discriminative performance. We know that they're scalable. Wonderful algorithms have been developed. There are some limitations. GPs, on the other hand, they can do the probabilistic tasks. They're suitable for hypothesis testing, getting confidence bounds, prediction intervals, and stuff like that. They are typically not scalable. Choosing that kernel, choosing this function, that K function on the previous slide, is actually a hard thing. So building a deep learning and a GP connection is actually something that could be pretty cool. It could combine strengths from both of these worlds. Bring in scalability with all the stuff that you'd actually need to make deep learning usable for science. It couples with what I've started calling the United Sciences of Data. You bring in all the data science streams together as you do this sort of stuff. So it's a wonderful world for me. Okay, there are actually many, many, many ways of linking deep neural networks with Gaussian processes. I've listed a bunch of them. I mean, you could read these slides later on, so I'll not really go over every single one of them, but I'll go over 3 really interesting cases. But the whole idea is that you could relate deep neural networks with Gaussian processes in many different ways. I'd point out to dropouts here. Everybody loves a dropout. It became Irengal thesis and its subsequent usage is now incredibly popular in the community. That is another way of relating deep neural networks with Gaussian processes. So here's the first of the three different ways in which you could tie in neural networks with Gaussian processes. And so that long list that I had on the previous slide, most of them were about relating the architecture of deep neural networks, the structure of a deep neural network, and relating that to Gaussian processes. This one is different. This one relates the training method, the training algorithm. So Arindam mentioned some time back, one of the standard techniques of training any neural network or any such complicated data science machinery, like even a lasso these days, is to go through a gradient descent, typically a stochastic gradient descent. So you look at your cost function and then try to go towards at least a minima or an accumulation point at least of that and hope that that's the global minima kind of a thing. So that's how gradient descent works. You could do a slightly different variant of a gradient descent called a kernel gradient descent. This sort of leverages how the network has been built. And that gives rise to something known as a neural tangent kernel. So this neural tangent kernel seems to stabilize if the width of your deep neural network tends to infinity. And this actually is a kernel relating to a particular Gaussian process. This is actually a different way of kind of relating deep neural networks with Gaussian processes, and it's something that we've been working on, and we are finding fantastic properties out of this. So here's an example, and I should mention these are all other people's works. Mostly, we've been reproducing some of it, but so let's say we have a supervised learning task, and here's the boundary that separates the two classes, the blues from the oranges on my screen. So this boundary is something that a deep learning methodology would actually find out for you. What a Gaussian process does is sort of gives you an equation for this line. Now just think back at what Laure was saying. This is about discovering equations. What this neural tangent kernel-based Gaussian process is also able to do is say that there's a lot of uncertainty about A or D, which are close to the boundary. Our confidence in saying B is blue or E is red is much higher. So far less uncertainty. That's how one of these things go. Here's a second DL-GP connection. This is known as NNGP, Neural Network Gaussian Process. We construct a fully connected multilayered perceptron, so your usual feed-forward network with random weights, biases. And then you move the whole thing through, except that you compute at the last layer, at the output layer, a kernel that corresponds to that. And then instead of using your stochastic gradient descent, you take that kernel learning and treat the output layer as a Gaussian process. Okay? That actually outperforms doing standard deep neural networks on here's some very standard data sets where it does very well. In all these cases, you'll see that the neural network GP actually does better, sometimes significantly better than the other ones. So this is, again, not our calculation. So the table is actually from the paper that reported this, but we've been able to reproduce this more or less entirely. Here's the third variety. So fully connected multilayered perceptrons The feed-forward networks are interesting, but people really use convolutional neural networks, LSTMs, and things like that. So where does Gaussian process sit in that perspective? Well, so here's what happens. So this is a bit more challenging. We have a low dimensional parameter essentially in a CNN instead of having too many parameters to work with. So some of the techniques of relating deep neural networks to Gaussian processes do not work. The other problem that comes up is that calculating that kernel, that all important kernel function, becomes incredibly hard. Also, when you're going to a realistic world, going to an infinite width or an infinitely deep neural network is a very unrealistic scenario. So here's something that has happened recently, and again, this we found a ton of interesting details here. Newer results I'm sort of postponing to our next workshop on this sort of stuff. So this is an idea due to Rasmussen and his team. And what I've presented here is a major oversimplification, but you essentially play with the position of the kernel filters as well as the filter values to a situation where it turns out that you could ignore tons of covariances, and the kernel recursions themselves become really, really simple. So there has been recent discoveries that relate convolutional neural networks to Gaussian processes. And so there's a ton of challenge. I mean, we know this. We've been able to get to that point with CNNs. RNNs are still an open problem. And here's something that, again, on MNIST dataset relates what a CNN GP is able to do compared to something that I showed you just moments back, NNGP. Now, this, you might say, improving on a decimal place here and there is not really a big deal. That's entirely true. I mean, this is not just about prediction, not just all about this last column where you show that you've improved on a second or a third decimal place. What these GP variants are able to do is that they are also able to tell you, give uncertainty bounds. So essentially say that this is significantly better than that one, and so on. Okay? So they are able to do uncertainty quantification at that level, which again is great. They are able to pick up the correct sort of features. So associate the kind of the univariate distribution, sort of like the ones that Laura showed you for those weights with her model. So something like that for every weight or sequence out here. Just to wrap up stuff, I see Michael has come on screen, so it's probably time for me. Again, just acknowledging all the grants, and thank you. I've got a bunch of references here for those of you who need to see the slides. So.
Okay. Thank you, Ansu. We do have a question. Many atmospheric processes are non-Gaussian and quite skewed. Is there an approach we can use with those sorts of systems?
Yeah, totally. So this is partially what I meant by saying that this is mostly an overview. This is a relationship that I'm showing you between deep learning and Gaussian processes. However, you could go to, this also relates to a question that was asked during Laura's presentation. You could go to extremes. You could go to skewed distributions. You could go to things that are built. So there are other stochastic processes that you could relate to. I would especially mention two that we are working with. One is what I call a randomly scaled Gaussian process, and the other one is what's traditionally known as an elliptical process. These are things that you could also relate to. There are So the GP, the Gaussian process, comes from a limiting argument. If you go into more terms and not just the limit, so the limit plus the next order term kind of a thing, you would be able to capture the skewness part of it and so on. So this beautiful mathematics and machine learning relationship that actually happens up there. So yes, certainly it can be done. It is being done.
Good. Thank you, Ansu. I'd like to thank all the speakers in this session for the wonderful job that they did, and remind people of the next session at 1:30. We do have a short announcement from Ray as to some technical details. Oops. Ray?
Thank you, Michael. Okay, yes, for anyone who is planning on attending our next session on aquatic sciences, you'll be using the same Z-link and YouTube link that you did this morning to access either the Zoom webinar or the YouTube stream. But be sure to refresh your connections to those links before the 1:30 session starts, as we will be updating their redirected links during the lunch hour. The Q&A Slido link, QRL, and the link will stay active. You do not need to refresh those links.
Okay, thank you, Ray. And with that, we'll go to the lunch break.